Welcome back to the Calculus Conundrums page on applications of derivatives by the perfect square. Feel free to subscribe if you like what you see here. This is just a continuation of the first derivative test, but this particular video is going to involve trig functions. So if you don't have any reason to study trig functions, then you can go ahead and skip this. So the function I'm going to look at here is the function sine squared of x plus sine x, and we're only going to focus on that function from 0 to 2 pi. So that we're just going to look at that interval. Now you can find the derivative of this. You can do this on scratch paper and just show that the derivative of sine squared x is 2 sine x cosine x, and the derivative of sine x is cosine x. And then if you set this equal to 0 and factor out the cosine x, you get cosine x times 2 sine x plus 1 equals 0. And then if you set the cosine x equal to 0, and remember we're only dealing with numbers that fall within the interval 0 to 2 pi, then your critical numbers for cosine x equals 0 would be x equal pi over 2 and 3 pi over 2. And then you also have to set this factor equal to 0 and solve it. And when you set that factor equal to 0, you get sine x equals negative 1/2, and then you determine that sine x is negative 1/2 when x is 7 pi over 6 or 11 pi over 6. So now I've put these in order here, and so this right here is pi over 2, this right here is 7 pi over 6, this is the 3 pi over 2, and then this is 11 pi over 6. So remember we're starting at 0, so the first interval would be 0 to pi over 2, and then if you pick a number in that interval like 1, you can plug 1 back into this derivative here, and so just plug 1 back into that derivative and evaluate it on your calculator and see what you get, and you'll get a positive number. So the derivative at 1 is positive, and then from pi over 2 to 7 pi over 6, that'd be the next interval, and the number 2 falls in that interval. So I can evaluate this function, the derivative, at 2, and when I evaluated the derivative at 2 on my calculator, I got a negative number. So now let's consider the critical number pi over 2. Notice to the left of pi over 2 the derivative is positive, and just to the right of pi over 2 the derivative is negative. So therefore we know we get a relative max at pi over 2 and whatever its functional value is. I didn't try to figure out the functional value, but if you want to, just put pi over 2 back into the original function up here, and then you can determine what the functional value is. Alright, now the next number I want to consider is at 7 pi over 6. So we already know to the left of 7 pi over 6 the derivative is negative. So let's figure out what the derivative is between 7 pi over 6 and 3 pi over 2. Well, 7 pi over 6 and 3 pi over 2 would contain the number 4. So we can take 4 and plug it back into the derivative, and when I did that I got a positive number. So I got a negative number to the right of 7 pi over 6 and a positive number to the left. I got a negative number for the derivative to the left of 7 pi over 6 and a positive number for the derivative to the right of 7 pi over 6. So that means that at 7 pi over 6 I get a relative minimum. So I get a relative minimum here at 7 pi over 6 and whatever f of 7 pi over 6 is. And now let's go to 3 pi over 2. We know the derivative to the left of 3 pi over 2 is positive. So we pick a number in the interval 3 pi over 2 to 11 pi over 6, and we get 5. And so plug 5 in to this derivative and evaluate it, and I got a negative number for of that. And so now that the derivative to the left of 3 pi over 2 is positive, and the derivative to the right of 3 pi over 2 is negative, so I get a relative max also at 3 pi over 2 and f of 3 pi over 2. And then the last one, critical number, is 11 pi over 6. And so 11 pi over 6, we know to the left the derivative is negative. And so if I pick a number to the right of 11 pi over 6, like the number 6, and I evaluate 6 at the derivative up here, I came out with a positive value. And so now, since the derivative to the left of 11 pi over 6 is negative, and the derivative to the right of 11 pi over 6 is positive, then I know I get a relative min. And that's at 11 pi over 6 and whatever the functional value is at 11 pi over 6. So those are the relative extrema there. Now, I showed here the open interval, so that way I didn't want you to have to worry about what was happening at 0 or 2 pi. Technically, if I had given you the closed interval, then you would have to look here and say, okay, at 0 we get a relative minimum, because that's the lowest point, in this neighborhood, and at 2 pi you would get a relative maximum, but that would be only if I was allowing the endpoints to be included in the interval. But there I purposely didn't allow the endpoints to be included, so we don't have to worry about those extrema at the endpoints. The next example is cosine x plus sine x, and again I'm looking at this at the closed interval 0 to 2 pi. So you'll see when I finish this, I'll actually talk about the endpoints this time. Alright, the derivative of this would be minus sine x plus cosine x, and if you look at a previous video, when you solve this and find out where this equals 0 on the interval from 0 to 2 pi, it's actually going to be at x equal pi over 4 and x equal 5 pi over 4. And so you can look at my previous example. I believe I did this in the increasing decreasing functions, in the videos for the increasing decreasing functions. And so if you go back and look, it'll show you how I got pi over 4 and 5 pi over 4. But anyway, those are the numbers that will make this derivative equal 0. So I break the number line up at pi over 4 and 5 pi over 4, and then I get the intervals from 0 to pi over 4, from pi over 4 to 5 pi over 4, and from 5 pi over 4 to 2 pi. Now, at pi over 4, when I plugged a number between 0 and pi over 4 in, like pi over 8, when I evaluated this at pi over 8, I actually got a positive number. And when I evaluated this for a number between pi over 4 and 5 pi over 4, like pi, and when I plugged it into the derivative, I actually got a negative number. And then I picked a number between 5 pi over 4 and 2 pi, which we could just say 6 pi over 4 is in there, which is really 3 pi over 2. So plug 3 pi over 2 into the derivative and evaluate it, and you get that the derivative at 3 pi over 2 is a positive number. Now, using the first derivative test, I can say that at pi over 4, since the derivative to the left of pi over 4 is positive and the derivative to the right of pi over 4 is negative, I can say that we get a relative max at the point pi over 4 and whatever f of pi over 4 is. And again, if you need the functional value, just plug pi over 4 into this to get it. And then for 5 pi over 4, the derivative is negative to the left and positive to the right, and so that means I'm going to get a relative minimum at the point 5 pi over 4 and f of 5 pi over 4. That should just say point, not points, but anyway, 5 pi over 4 and the functional value 5 pi over 4. And if you look at the graph, notice here's pi over 4, there's your relative max, and here's where 5 pi over 4 is, that's your relative min. Now the x values aren't your max and min, so I didn't give the y values, but the max and mins are actually the y values. Now the other place, since we are including the endpoints here, I can actually say that you get a relative minimum at x equals 0, and you get a relative maximum at x equal 2 pi. And the reason is if you look in this neighborhood, this point is the lowest point on the graph in this neighborhood, and if you look in this neighborhood, this point is the highest point of the graph in this neighborhood. So technically the endpoints also yield relative extrema. Okay, so that takes care of relative extrema, and I believe the next video I'm going to cover a couple of theorems, and then from there I'm going to go on into concavity after I cover those theorems. Oops, I forgot. I have some practice problems here if you want to do these for practice. Here are 4 practice problems, and then you can determine what the relative min and the relative max are for each of these, and using the first derivative test, and you can check the answers because I'll give you the answers over here. Okay, so now we'll go on to the next video over a couple of theorems, Rolle's theorem and the mean value theorem.